Welcome to the office. We want to take a look today at a proof for the volume of a sphere. Of course, the formula here. So we want to consider three objects for our proof. What we're going to consider is a hemisphere of radius r, a cylinder of radius r and height r, and a cone of radius r. So below these three images show essentially a side view of what we have. So this is our hemisphere, that is the upper half of a sphere. So I suppose dash this part of it, you wouldn't see. And here, this is a cylinder of radius r, so a side view of a cylinder. Just looks like a rectangle, of course. So there we go, dash that. Here's the top. And there we have a cylinder. Of course, the radius of this cylinder, right from here to here, is r in this case, and its height for each of them. Each of these things has a height of r. Hemisphere, of course, from the center to here is a distance of r. And then here we have a cone. This cone is upside down for how we normally think of it. We normally think of the base, that large circle being at the bottom, and then going up to a point at the top. So it's just upside down side view right here. Again, we have a radius of r for that base. So from here to here, we get a distance of r. And what we have to rely on as we develop our formula for the volume of our hemisphere, or sphere in total, is that um, we actually have the formulas for volume of a cylinder and the formula for the volume of a cone. Okay, we're going to assume we have the formulas for those two things, and then we're going to come up with the formula for the hemisphere, and then we'll use that, of course, just doubling it to get the full sphere. All right, so what does this look like? Well, if I wanted to find these volumes, one typical way is to integrate, right? If we recall, this takes calculus, so 2 here. So if we integrate over area, dx, d whatever, if we integrate over area, see, suppose I want cross-sectional area into it. Well, anyway, what this gives us is this gives us volume. So when I consider the cross-sectional area here for the hemisphere, here for the cylinder, and here for the cone, I can integrate over those areas to give me the volume. Now, we're not actually going to integrate because we already know these formulas, but we want to get this relationship established through these cross-sectional areas. So what I would have to do is, of course, a cross-sectional area of a hemisphere is just a circle. So we know the area of a circle is given by pi r squared. So we just have to figure out the radius of, not the hemisphere, but the radius of this circle. So if I call this distance x, of course, all right, so here we have a triangle very nicely. This distance would be h. I know r and h, right? Those are fixed numbers. And if we call this distance here x, we can find that using Pythagorean's theorem. So we would know that x is equal to the square root of the hypotenuse squared minus the height squared. Okay, so this gives us a formula for the value of x, and then we can find the area of the slices, so cross-sectional area. Cross-sectional area. Cross-sectional area of this circle is pi r squared, so area is equal to, and actually we use a fancy looking a here if I can draw that. That's not quite what I want either. There we go. Fancy looking A. Okay. So area here, of course, is pi r squared. R, not this R being the radius of our circle. So x squared, and x squared here is the square root of r squared minus h squared being squared. All right, here we have, right, the cross-sectional, a cross-section of a cylinder is, again, just a circle, but the radius in each case is the radius r of the cylinder. So the area here is going to be given by pi r squared, actually r squared. Wonderful. And the cross-sectional area here, well, again, if we recognize that this distance is r, that means, of course, oh, maybe let's draw the triangle over here. So we have this distance is r, this distance is r, which means this distance, of course, is r. So I have here a right triangle. And if I wanted to determine what this length here is, oh, let's see here. Create a square. How do I want to describe this? Oh yeah, okay. Well, I suppose we didn't need that. My apologies. So if we think of how we're moving upwards here, since this is length r, this is length r, this is length r, we have that these lines are going up at the same rate that they're going over. That is, as I move up by h, I'm moving over by h. So the radius here of our cross section, right? Our cross section, again, a circle, our radius of our cross section is also h. So the area of that cross section is pi times the radius of the cross section squared. Fantastic. Now notice here that we can express square of a square root pi times r squared minus h squared is equal to pi r squared minus pi h squared. We get this by, of course, distributing the pi into the parentheses. So we get this relationship between the cross-sectional areas. That's absolutely beautiful. Once we integrate, then integrate over h, that is values from 0 to, I'm sorry. Yeah. Integrate over h. That guy. 0, so we're integrating from 0 to h, the height of it. And once we do that, that will give us exactly the volume of the hemisphere. So V sub hemi is equal to, when we integrate over this thing, that gives us the volume of the hemisphere. When we integrate over this thing, this gives us the volume of the cylinder. So volume of the appropriate cylinder minus the volume of our cone. So the volume of the hemisphere is equal to the volume of the cylinder minus the volume of the cone. Sweet, right? We didn't actually have to do any integration here. We just have notationally what's going on, which is wonderful because what that gives us is it gives us formulas that we already know. So this is going to be pi r cubed minus pi r, 1/3 pi r cubed. And of course, that's simply equal to here, I have a whole one of these things minus 1/3 of one of those things. So 2/3 pi r cubed, right? Pi r cubed. A whole one minus 1/3 of one leaves us with 2/3 of one. So if I double that, then that's going to give me the volume of the cone. And when I simply double this, so we get 4/3. Sorry, not the volume of the cone. What am I saying here? The volume of the sphere, right? The volume of the whole thing. I double it to get the whole volume. Sphere. There we go. The volume of the sphere is 4/3 pi r cubed. Again, double what we get for the volume of the hemisphere to get the volume of the entire sphere. Double the formula. Instead of 2/3, 4/3, double, right? So there we go. We get the volume of the sphere. Excellent. So we're going to pause here for now, and we'll take a look at a proof for the surface area of a sphere as well. Of course, the formula. So join back here in the office in just a little bit.